education. And in this week we started with register spelling. So in the previous week we were talking about how the system has a limited number of registers, and in our IRs we have an unlimited number of temporaries. So in this particular scenario, if we do not have, uh, let's say, a many-to-one mapping uh, which kind of satisfies the constraint on the number of registers, we need to spill some registers to the memory. So then what we came up with was that we had this very nice graph coloring algorithm, where we colored the graph with K colors, uh, and if there is such a coloring, we have got a mapping uh, where we assign one color with one register. But now if suppose we do not have that particular kind of coloring, then what we came up with was, let's say we need to make the graph more sparser, reduce the number of edges. So what we do is we pick a node and we remove it from the graph, and it's all over edges, and we somehow make the graph more sparser, and thus we can somehow and then we can, let's say, think that okay, the graph is more sparser now, maybe we can color it with K colors. So then we talked about, okay, what are some examples, what are some valid reasonings to pick up a node. So the first we came up with was, okay, pick the node with the maximum degree, because it would somehow make the uh, graph more sparse, most sparse one at a time. But then we came up with this notion that, okay, that picking up a node just by looking at that particular graph does not uh, is not guaranteed to give a very good uh, register allocation. Why? Because that graph may be that node might be used in a lot of our code, and basically if we are spilling it to memory, we are increasing our latency, which we do not, and if that particular variable uh, is getting used a lot, we would definitely not like that. So the second thing we came up with was, pick a node which has the minimum live range, and we define live range as the number of program points in the whole program where the variable is live. But then once again we came up with this notion that, okay, what it's statically it might be very less, but let's say if that program point is in a loop, and if it is used in a loop, let's say a million times, then it becomes a problem, right? And then we came up with this notion of hot regions and cold regions, and we thought that, okay, let's choose the variables which are in the cold regions first, and then remove them and then color the graph. And then we came up with the notion of optimistic coloring. So then we start in that, basically what we do is we pick up a node. So given that we are not able to color it in K colors, we pick up a node and remove it from the register interference graph, and we try to color it with the remaining colors. And if it is not possible, we again try to remove some other nodes, and when it is possible to color, we then try to add it again in the graph, if possible. And thus if it is and then we saw an example where we actually had to remove variable nodes A and F initially, but then when we colored the graph, we could add uh, another add back A but not F. Uh, and then basically we talked about how to spill. So if we know that, okay, F is gonna be spilled, how do we do code generation for it? So we just talked that whenever uh, so we allocate a memory location for F, let's say FA, and before each operation that reads F, we do F is equal to load FA, and after each operation that writes to F, we do store F comma FA, basically storing the value of F to FA. And we also said that we should rename each use of F to F1, F2, F3, because we are storing and loading values, and at different program points these are different values. And since now we have these renamed versions of F, namely F1, F2, F3, we have a different So we said that the rig now is more sparser because it's not just one variable. We have different variables for the same variable at different program points, and thus we can satisfy that coloring as well. Uh, and then we came up in the next module, we came up with the limitations of graph coloring. So the basic limitation was that it was static. So let's say if one variable t1 is getting used heavily in a loop in one region, which is a loop. So then we want that register T1 to be in the variable T1 to be in the register, whereas in the second region where it is just it's in a if then else branch, we do not might not like it to be assigned to a register because it might not be used so heavily as in the loop. So then we came up with this idea of region-based register allocation, where in one region we allocate one set of variables to registers depending on uh, how heavily are they used, and in this next set of regions where that particular maybe there's some differences in the usage, we allocate the registers accordingly. And then we at the boundaries of the regions we do this necessary translation that is required to do that, uh, basically for the correctness of the code. And so there is definitely this overhead of uh, this translation at boundaries. So we do not want a lot of regions as well in our code, but at the same point of time, this regions do give us a benefit, as discussed by this example of a loop and an if-then-else condition. And there were some more limitations that were discussed in the module, basically that we need to do instruction selection later in the code. So what is happening right now is we are doing register allocation, and then the code then the compiler does instruction selection, but instruction selection might only happen in some particular register values. Let's say in MIPS, what happens is that a multiplication or the add or subtract is only done on registers. So let's say if we have done let's say a multiplication on A cross B, where A is actually spilled to memory but B is in register, then it becomes a problem. So then we need to somehow go back to see if we need to basically correct it again, because that's not allowed by the architecture. And this was something known as reloading passing GCC registers allocator, which was like said. And there was this alternate approach that was discussed, that what we can do is basically do register allocation and instruction selection simultaneously, and that is somehow we can uh, reduce that coming back to it, and so that it might also be efficient. So this was basically the 85 to 86, the 86 to 87 lecture modules.
Okay, great. Thanks, Jay. That was a very detailed and very nice summary. Samir, do you want to go for the next 3 modules or?
Yes, sir. Okay. So earlier, till now, in all the DFA representations that we discussed, we were talking only about single variables and how we do analysis only for single variables. So so as discussed in previous modules, that if we use more than one variables, then we can improve the precision and efficiency of our DFA. So for that, we will need alternate DFA representations so that we can improve our efficiency, and we can also develop a common framework and common set of structures for the DFA. So the difference between this alternate form of DFA is that we will use the information with the help of sets. for example, earlier for a variable, we will storing that the value of a variable is either top, bottom, or constant. But at each program point now, we can maintain a set that contains the values of multiple variables in the form of tuples. For example, a tuple can consist of a variable as the first element and the expression or a constant value that is assigned to it at that point at that program point. So and then we discussed how we are going to do it. We discussed an example. For example, for each program statement, there are 2 points we are defining. One is just before it, that is we call it that in point of the statement, and the other is called the and the point just after it is called the out point of that statement. And this is while the out point of the first statement is similar to the in point of the next statement, but we are using different names for the sake of notation in this case. So yeah, so after this, what we saw is that how different precision functions can help improve the precision of our DFA. For example, if we use a complicated precision function which can use for inference as well. For example, we have an expression x is equal to y plus 3, and at the inset we have information about y as well, that y has the value 1. And if we have an more intelligent precision function, then we can infer that x is equal to 4 because y is equal to 1 and x is equal to 1 plus 3.
Just wanted to say, did you mean transfer function?
Yes, transfer function. Sorry. Yeah. Yeah. So we saw and after that we saw a notion of a meet function. So what happens that if there are multiple incoming edges to basic block, then we will need a meet function which can give us this set with the help of which can give us the inset based on the outset of all the incoming edges. So as we saw that it is earlier, that it is usually the greatest lower bound of all these greatest lower bound of the all the outsets of all the incoming edges. And usually there is and for that we need to define some notion of partial ordering as well. After this, we saw that in most of the cases, the transfer function can be represented in the form of outset is equal to inset minus kill set, and take the union of this with the gen set. So and this kill set and gen sets are usually dependent only on the statement, and it can be pre-computed. And so what the idea of behind kill set and gen sets is that all the definitions that a particular statement removes is denoted by the kill set, and all the definitions that a particular statement introduced is a part of the gen set. Therefore, we remove the kill set first, and then we add the gen set. Then we saw examples of gen set and kill set for constant propagation, in which the gen set is for a constant assignment is just a single set with single element, that is x comma the constant value, and the kill set is x comma dash x comma dash, which means that all the values of x that were assigned in point are being removed because we are assigning a new value to the x at that point. And similarly, we saw an available expression analysis. So available expressions analysis is type of a DFA in which we try to maintain not just the constants but also the expressions that are available for multiple variables. For example, even if we have x is equal to y plus z, then we will try to maintain that our variable has that value. And yeah, we saw that example, and after that we saw one property of this gen set. We saw that the transfer functions for each statement in a basic block can be composed sequentially, so that we can get the transfer function of an entire basic block. And we saw how we did some analysis, and we saw that how we can represent the transfer function of the entire block in terms of gen sets and kill sets of each individual statement. After this, we saw another type of analysis, DFA analysis, called reaching definitions analysis. So the basic idea behind it, reaching definitions, is that we don't we also keep the values that are definitely there for a variable, but we also try to maintain the values that might reach at that point. Unlike a previous analysis, at which if a particular value is available for a variable in a set, then it is definitely there. But in reaching definitions, we are not sure that it is definitely there, but it might be there. So we are trying to kind of maintain all the possible values that are present. So we did that kind of analysis, and we then introduced the notion of kill set and gen sets for for reaching definitions analysis as well. And we saw the meet function. So earlier, for available expressions, the meet function was the intersection, because we needed to be sure that intersection of all the output sets of incoming edges. So that was there because we wanted to be sure about a particular value. But in case of reaching definitions, it is union, because we are just trying to see what values can be available for the variable. Apart from that, we saw how in reaching definition analysis is that we saw an example for in which there is a loop, and inside a loop, multiple values, two or more values can reach for a particular variable. And we saw that sometimes it is helpful to just split the loop for two particular cases of values of of a variable that is reaching inside the loop, because loop is the part of the code that is often executed a lot of time, and the part of program which is run for most of the time. So if we can specialize one of the branches by setting by doing some optimization like constant propagation or something, then we can optimize a part of the loop, and we can potentially save some operations, and which in turn can help us save a lot of time, which can create a meaningful optimization, because that particular part of loop is run for most of the time. So that's it for till module 90.
Okay, thanks, Amir. Anybody wants to go for 91? So,
in module 91, we talked about DFA framework. So here we talked about first we talked about that there are two types of DFA analysis: forward analysis and a backward analysis. In a forward analysis, a transfer function will take the in value of a statement to the out value of a statement, whereas in backward analysis, the transfer would be from out of a statement to in of a statement. Similarly, with a meet operator, that in forward analysis, they would the meet operator would make it in of a statement as a combination of out of its predecessors, and it would be just the reverse for backward data flow analysis. So then we said that DFA equations must hold that even in presence of cycles. Then we talked about that there is a partial ordering among these values, that if in an iteration A changes to B, then this must mean that B is less than equal to A. Then we said that for a DFA, the input is a control flow graph which has the number of nodes, uh, an entry node and exit node. Then we saw the example of constant propagation. We said that the out of the entry node is set to an empty set. This is the boundary condition. And for each initially for each basic block other than entry, we set the out of that basic block to a top value. This is the initialization condition. And till any changes in out occur, we just keep iterating and specify and apply these meet operator and transfer functions. So basically, then we just discussed the summary that for constant propagation, domain is a set of constant definitions. Its direction is forward. Its transfer function is that out of basic block is a function of in of basic block. The meet operation is the set intersection, and the boundary condition is that out of entry is an empty set.
Okay, wonderful. Thank you. Thanks, Arpit, and thank you, all three of you. This is great. So yeah, let's start with some questions on, I think you have covered a lot of ground in these lectures in the sense that we are already familiar with DFA. We kind of, dwelled on DFA a lot, but also, there's a kind of completely different topic, which is about register allocation. Also, I assigned one module, which was basically framework, which Arpit summarized, which I wanted to kind of also discuss so that because next week we're going to be looking at all the modules related to framework, so we can just also just wanted to introduce you and kind of clear some initial doubts so that we can be all set for next week. So yeah, please go ahead. Questions. Sonu.
Yes, sir. So I think in the modules you talked about transfer functions and meet operators doing this operation at a statement level, and then you combine these operators, and the operation was done at basic block level. So I wanted to understand, the differences between doing these operations at basic block level and statement level, or are there advantages, disadvantages between two, or how are they interconnected in the sense? I mean, there is a mathematical operation that we do, but other than that.
Okay, that's a good question. So basically, the question is, whether I define a transfer function at statement level, or should I define this transfer function at the basic block level? Does it matter from a precision point of view? Does it matter from an efficiency point of view? So first of all, let me tackle the second one, which is efficiency. And it's easy for me to claim that it's actually more efficient to actually, do transfer functions for the basic blocks, because you're going to be applying the transfer function over and over again in your DFA fixed point iteration. So if you summarize the entire basic block as a single transfer function and have a more efficient representation of it, for example, I showed the example of gen and kill and how gen and kill can compose to make a gen and kill for the entire basic block, right? And so that way, just kind of summarize the individual gen and kills into a single gen and kill, and then you just apply that in one go. And so, if there were 10 instructions in your basic block, then you kind of reduce work from 10x to 1x. So there's an obvious efficiency benefit to actually doing transfer functions at the basic block generality. Now, what about precision? Does it increase or decrease precision? So my first point is that it does not decrease precision. It can only increase precision. In many cases, it makes no difference. For example, in the gen and kill case, it won't make any difference whether whether you compose or whether you do separately, you're going to get the same answer. And that's just by the construction of the transfer function, because it just doesn't matter, whether you apply it separately or whether you just summarize, it's actually the same thing, because that's just by the construction of how we are constructing the gen and kill for the entire basic block. But then there are transfer functions where the summary transfer functions may potentially be more precise than the individual transfer function. So I'm calling the summary transfer function the transfer function of the entire basic block, and then the individual transfer functions are the individual transfer functions of each statement. And there are possible transfer functions where the summary transfer functions can potentially be more precise than individual transfer functions. And here's an example. Let's say I'm interested in constant propagation, and let's say in my basic block I have two statements, y equals x plus 1 and x equals y minus 1. Right? Now, if I basically use individual transfer functions, then let's say, if my incoming value was constant 3, then if I use individual transfer, hold on, okay, maybe this example wasn't, well, yeah. So it is possible that, my transfer functions basically miss out on certain things. So it could be, for example, instead of x plus 1, it could be y equals x plus z, and x equals y minus z. So eventually, basically, x is remaining unchanged across the basic. But in the middle of the basic block, x is not a constant, because it's y plus z, and then, I first add z. So x equals x plus z, and then x equals x minus z, right? So if I look at the summary transfer function, it's as though x hasn't changed. And it's possible for me to have a summary that's more precise than the composition of the individual transfer functions. Right? Because if I just compose the individual transfer functions, I would have said, oh, x is not a constant in the middle, and then x is not a constant at the end. But if I use the entire basic block, then I can say that, okay, I can kind of use some more sophisticated analysis to generate a better transfer function. And that's basically depending on how am I generating the summary. So in my lecture modules, I discussed how to generate a summary for gen and kill sets. And that way of doing summary was not giving me any extra precision. But then, I could potentially have a method to do summary transfer functions for the entire basic block that gives me extra precision. And actually, I should point out that we're going to discuss this whole business of summaries and transfer functions and stuff like that later in the course. It's called region-based analysis, and it'll come later, and we're going to discuss in a lot of detail. So even if everything is not, even if you still have lots of questions, I would just say let's just hold on, and we're going to learn more about it.
Okay, sure. Thank you.
Thanks. Okay, let's go to the next question, and I believe that's Akshin.
Yes, sir. So in the register allocation module, we said that, okay, we'll have a rig and then we will just try to see if it's K colorable, if you have K machine registers. But I think this was also mentioned in one of the modules. That's assuming that all registers are equal in some sense, right? Because in x86, I think RAX is called the accumulator. So instead of doing add RAX, RBX, you can just say add RBX, and that reduces the instruction size. There are also some other x86 registers, I think, that have special purpose. So how would you accommodate for that?
Okay, so the example you gave wasn't very clear to me. You're saying add RAX. Is that an instruction? What does that mean? Add RAX doesn't.
No, RAX is an accumulator, right? So if you do add RAX RBX, and it means add the value of RBX to RAX, you can just say add RBX. You just give one operator.
See, that's just a matter of syntax, right? I mean, whether I say add RBX and that's just going to accumulate into RAX versus I say add RAX RBX, semantically they are both identical and they're both going to use two registers.
Yeah, but the code size gets reduced.
It's not showing it as RAX, but RAX is kind of the implicit register here. And so from a register allocation point of view, it doesn't really matter. You still have to allocate one value to RAX and one value to RBX. So RAX is still getting used, right? So I just want to point out that the example that you gave wasn't the most accurate example for the question that you're asking. Do you agree with that, or?
Well, I was thinking, since the code size gets reduced, right? Since you only have one instruction, you would encode less information, which means the code size gets reduced and you potentially might have a speed up.
Oh, okay. So you're saying that, maybe it's better to have, okay. I see. So you're saying that some registers may be faster and some registers may be slower. For example, RAX may be faster, right? Is that what you're saying?
Yeah. So if I'm saying if a value is going to be added upon a lot, it's better to have that in RAX and then potentially reduce the code size.
Okay. Okay, that's an excellent question. So indeed, some architectures may have asymmetric access latencies for different registers. But fortunately, from a compiler developer's point of view, such architectures are rare. And in fact, x86 has symmetric access latencies. It doesn't really matter, whether it's RAX, RBX, RCX. It's just that it's a historical reason, legacy reason, that some instructions have RAX as an implicit register, but that doesn't mean that RAX operations are going to be faster than RBX operations. Okay, so that's a simplification, and as a compiler developer is happy with that simplification, because otherwise it would have made things more difficult for the compiler developer. But then you are right. I mean, there are some registers that are kind of special purpose. For example, on x86, there's a divide instruction, which requires one of the operands to be in RAX. So I cannot just say that, divide, RBX, RCX, RDX. I need to have one of the operands in RAX, so, and which one, there's some detail on what operand needs to be in RAX and so on. But, and even the result will be produced in RAX or something like that, right? And now that causes some issues for our register allocator. And so, as I've discussed in the module, this is pretty complex now, right? I need to kind of lower my IR into the x86 world or any other architecture which has these constraints that certain opcodes can only work on certain things. And the typical approach that is taken is that you just layer things. First, you assume that you can do it in any. So you have abstract registers for x86. You don't really give them names, but you say that there are 8 abstract registers or 16 abstract registers, you really don't give them names. And it's the next step when you actually start giving them names and say, okay, this register RAX, this register RBX, this register RCX, and so on. And at that time, you can do some intelligent thing and say, okay, let's look at the most constrained register. So, I just had like 16. Now I have lowered my IR into x86, assuming there are 16 registers, but I haven't really given them names. Now I can figure out, what is a good naming so that most of my constraints are satisfied. It's possible that when I give the naming, my constraints still don't get satisfied, or I'm not able to find a heuristic naming. Once again, it becomes a hard problem to basically satisfy all the constraints. It's a constraint satisfaction problem. And so it's possible that you're not able to do it in a limited time, or maybe it's not even possible. Even if I had all the computational resources, maybe it's not even possible to satisfy all the constraints. In which case, you're going to do another level of spilling at that level. Okay, and so you can say, okay, by the way, I need this register in RAX and I need that in RAX simultaneously, and so I'll have to spill one of them, put this in RAX, and then later bring it back, and then so I'll have to do it at that level. But all effort is made to avoid such spilling, and based on kind of trying to satisfy the constraints without having to spill. And so that's the next step. I mean, when we are talking about register allocation, I'm typically not talking about register naming, right? And then register naming is the next step of it. Also, I talked about how GCC does a reloading pass at the end, right? I mean, that's basically exactly this kind of thing, right? So these are all kind of, just layered architecture. And then for the corner cases, you basically do special things and you pay a price for that. Okay, thanks for the question. Shubham?
Yeah. So during register spilling, we defined a criteria which is a combination of two different criteria, and one of them was to spill the register with minimum live range to reduce the downside of our spilling. But the point I want to make is that it might not be the best option to reduce the to reduce to look at live range even for acyclic graphs. For example, if we have a code, acyclic code in which we define a variable at the entry point and access it at the exit point of the program, it would have a very big live range, but it it is not accessed many times. So instead of live range, if we uh, uh, if we look at the memory accesses of the variables, would it be a better strategy?
Okay. Did you say memory access of the variable?
No, not the memory access, but the number of times a variable is accessed.
Access frequency. Okay, yeah.
Yeah.
Okay, yeah, valid question. And indeed, I can kind of, I thought I kind of tried to explain this weakness of these potential things. And you're right. I mean, you gave me another nice example where, my heuristic of doing live ranges is not going to work because it's going to, if there's a variable that's used very seldom, only the beginning and the end, then I'm going to probably keep it forever. And that's not a good idea. I'm going to block one register. I could have spilled it. Typically, what is used is a combination of all these different things, right? For example, if something is being used in the beginning and something then it would have very little, so it will have very few number of incident edges, and so that way maybe that in that sense it would get picked up. But more importantly, the region-based analysis hopefully will help us out in such situations, right? The region-based analysis divides the program into different regions. Says that, okay, in this region, I'm going to use a different strategy from that region. And so that basically avoids the problem that a long allocation of the same register kind of interferes with the hot registers and that kind of stuff. And that to me is the most promising solution for the problem that you mentioned. There have been also other kind of proposals to do better register allocation. Some of them are dynamic programming based. If you recall dynamic programming from your algorithms class, they give you better optimality guarantees than the other heuristic based approaches that I just described. But then they are also more expensive, and so typically they are not at least in your typical compiler they are not used. But if it's a more kind of more performance critical, more optimizing compiler, then these kind of approaches are also very common. Did that answer your question, Shubham? So, okay, thanks.
I wanted to claim that wherever we are using this intuition of
in this intuition of live range, we can replace it this intuition of a minimum accesses to a variable. Uh,
Uh,
if we just look at, if we for the case ignore the region register allocation and just look at a basic block in which we are applying this algorithm. So
okay, so you're saying that it's a strictly better thing to use access frequency than using live range.
uh, I'm
Uh,
just asking if it is a possibility.
No, definitely access frequency is definitely part of the game, right? Because I mean, when we say that if it's being accessed in a loop, so we are basically trying to create an estimate of the dynamic access frequency. So basically, what we really care about is the dynamic access frequency, and that includes, if it's an acyclic graph, then it includes the static access frequency as well. So it's not just about whether it's in a loop or not, but even inside the loop, if it's been accessed twice, then it's more important than if it's been accessed only once. So we basically try to estimate the dynamic access frequency. And maybe I didn't maybe I didn't say that in as many words in the module. But yeah, when I'm saying that on a loop, and maybe access a million times, I'm really trying to estimate the dynamic access frequency, and that would include the static access frequency as well. So you have a valid point, and that's where it gets covered. Okay. Jay Arora.
Yes, sir, I have a doubt in optimistic coloring. So we picked a node by some criteria. The node was n, and then we recursed on the remaining graph. And so in the example which you showed, it was like we picked A, then we picked F, and then after that we landed up on a graph with 4 nodes, and we straight away said that it was recolorable. So I mean, so how do we figure that out? Do we recurse till we get a graph of let's say k vertices, where we can surely say that it is k colorable, or let's say do we do some other checks in between?
So yeah, graph coloring is an NP-hard problem. So we need to use some heuristic to basically figure out what the coloring needs to be. We can basically say, okay, we can use some kind of greedy approach that, if for every snapshot, we just try our greedy approach to try and color it. If we are able to color it, we are done. If we are not, then we basically try to spin. I mean, that's how the algorithm is proceeding, right? So does that answer your question, or?
I mean, so I mean, basically, we would recurse till, I mean, let's say if we have k machine registers, so basically we would eventually recurse till the point where a graph has k nodes, right? Where we would directly say
Yeah.
that it is k
Exactly. I mean,
colorable,
as
and
soon as
then
it's very clear
backtrack.
that it is, I mean, as soon as we have only k nodes remaining in the graph, it's very clear that it's k colorable, right? And we can just stop there. Yeah, so that can be the termination point. Absolutely. Yeah, thanks. Rahul Kanya.
Yes, sir. Good morning, sir. Sir, these optimizations seems to be like pretty complex and would take a lot of time. So, is there a way to calculate or predict like theoretical maximum or minimum speed up or performance improvement that we'll get, so that we can decide whether to use or not any optimization level, or is like we have to do optimization then only we can know, or is there a way?
No. So, I mean, all these optimizations are based on some cost model, right? That, what do I think about how much improvement it's going to make? Because, a compiler has no visibility, at least, most compilers, like most compilation environments, there's just-in-time compilation and all that, which is different. But if ahead of time compilation, the compiler won't know, how much time has been saved by my optimization. The compiler is just making a guess. And that's based on a cost model. For example, if it's saving an instruction, maybe it's saving one cycle.
No, sir. So the question was ki whether it is possible to like approximate how much will save, so that we can decide. Now, suppose like if it is like only 5% speed up or something, and we are taking like days to optimize, so we can decide to not optimize, or like a theoretical maximum based on some number of maximum will change, maximum equations will
You're
change.
saying, is there a theoretical uh, lower bound to? Are you interested in upper bound or lower bound? I don't know.
So any bound that means maximum it will.
Theoretical upper bound, let's say,
Yes,
to
sir.
the improvement that this optimization can produce.
Yes, sir.
Well, there are theoretical upper bounds. There are also theoretical lower bounds, but those lower bounds, sometimes the bounds length could be pretty big. And first, most importantly, like bounds don't matter. What you care about is the average case. And so, it doesn't matter, in the best case, what would have been the improvement? It may look very nice, but what's the point? Like if it's not going to be executing in the best code, or in the worst case, that's what's going to be the improvement. And that way we were just going to miss out on some optimization. So typically compilers don't worry about bounds in improvements. They just worry about, and secondly, it's, yeah, so typically compilers don't worry about bounds and improvements. They basically try to estimate what would be the average case improvement. And so they would use heuristics like, an instruction is a cycle, a memory access is, let's say, 5 cycles or 10 cycles, whatever, or it's going to try to estimate that a loop is going to probably execute at least 10 times or at least 100 times. And so based on these kind of estimates, it's going to figure out whether, doing this is better or doing that is better, where to invest my time in. And indeed, the compilation time is a big deal. No, I mean, today at least compilers don't take days to compile. I mean, compilers are supposed to finish in seconds, if in minutes, if not seconds, right? So, yeah. So all algorithms are time bound. I mean, in a compiler typically, and if there are some cases where even in the parsing stage, for example, C++, it's known that just parsing the syntax can take a long time. In which case, actually, the compiler is programmed to time out after some time. The compiler shouldn't take more than a certain amount of time. And if it is taking that much time, and this is not even about optimization, just parsing can take a long time. And if it takes that much time, you just basically say, just give an error, say I couldn't compile. Okay, thanks. Javeria?
So I had a follow-up to Shubham's question. So Shubham gave us an example where X is initialized at the very starting and it's only used at the end, and it has a live range of like basically the full program is a live range. And you somehow suggested that that we divide it in regions and do region-based allocation. But even if you do region-based allocation, X would still be live in all the regions, right? So then we won't get any benefit.
No, so when we do region-based analysis, right? I mean, I'm hoping that there'll be a region in the middle that is not going to have any access to X, right? So in the register interference graph, I can basically say, okay, in this particular region, I really don't need to register allocate X at all. I can just keep it in memory. Right? It's live,
Okay.
but it's not being used, right? So.
Okay, yes. Okay.
Arpit?
Yeah, so when we discussed how to spill, we said that like we were assuming that there is a register in which we can load the spilled value into. We said that like we can perhaps reserve a register just for this. I wanted to clarify this, that are we like reserving a register throughout the program to like say that this is the register in which loading and storing will occur through, or did that mean something else?
Yeah, so there are multiple strategies possible. It is, some compilers will potentially do, if they find that there is some places where they need to be spilling, they can say that, okay, this register is meant for spilling, it's not going to be used for anything else. If there's lots of spilling in the code. The other option is that wherever there's spilling, you basically, you just spill some other thing to memory, free up a register, so either you pay more cost at the spill location by kind of making space on the fly, or you pre-allocate the space, the register space, right? And there's a trade-off, right? In one case, you're reserving the space all through the program, but you are paying less cost at the spill location. In the other case, you are not paying much cost throughout the program, but then you are paying more cost at the spill location, because you have to kind of create that register space to be able to do the spilling.
Right. And I had another doubt that this cold and hot region analysis, would that be like done much better by a just-in-time compiler?
Absolutely. So this is exactly where a just-in-time compiler wins a big time over ahead of time compiler, because it's very easy for a just-in-time compiler to identify hot and cold regions, and this is one of the big advantages, one of the biggest advantages of a just-in-time compiler. right? That it knows, it can figure out what is hot and what is cold, whereas an ahead of time compiler can only make guesses. And typically an ahead of time compiler makes guesses based on the loop structure of the program. It just assumes that if it's a loop, then it's likely going to be executing more than, let's say, 10 times or at least, or something like that. Shubham?
This question is related to DFA. So when we run DFA algorithm for blocks instead of instructions, do we have the information about variables only at the block heads and block tails?
Okay.
Or do we have the information at every instruction level?
Okay, that's a great question. That's a, yeah, absolutely. That's a very good follow-up question to what Sonu asked earlier. And indeed, if I summarize the entire basic block into a single transfer function, then I'm only reasoning about beginning and end of the basic block. But what about in the middle of the basic block? After all, there are instructions in the middle of the basic block as well. Now, so and you, for example, if I'm doing constant propagation, then if there's an instruction that says x equals y in the middle of a basic block, then I'm really interested in what's happening in the middle of the basic block. I mean, it's not enough for me to know what's happening in the beginning of the basic block and the end of the basic block. So the way this works is, you basically first do, and this is going to be once again covered in more detail when we talk about region-based analysis later in the course, but I'm going to give you a quick summary, which is that, you basically have a summary transfer function for the entire basic block. And so based on that, you quickly compute all the in and out for the basic blocks. And then based on those in and outs, now within a basic block, it becomes easy to, whatever is the in of a basic block, you can just kind of transfer that across every single instruction, because you haven't lost the individual transfer functions. You just summarize them into a bigger transfer function for the entire basic block. But now, once you have done the DFA for the entire program, now it's possible to use, for example, if it's a forward DFA, then it's possible to use the in value at the entry of the basic block to compute the in values at every statement of the basic block by just applying the individual transfer function in the second stage. In the second stage, so after I've done the DFA, I've got the in and out values of all the basic blocks. I can use those in and out values to compute the intermediate values in the middle values of the basic block. Okay, excellent questions. Okay, I see a question from Gandhi Sanket Sanjay Kumar. Sir, in register spilling, can we combine some load and store of spill register to make it block operations? For example, if instructions are as follows and register F is spilled, X equals F plus 1, Y equals F into 2. Instead, making two load can't be one load optimized. Okay, absolutely. So after I have done my spilling, I can do optimization so that I don't have to save the store and load operations and combine them into a single operation. And this is where the local optimizations really help out, right? And so recall the peephole optimizations that we discussed about, that if there's a store followed by a load. And so I also said when I was discussing peephole optimizations that peephole optimizations are especially very effective at the end of the compiler pipeline so that it can clean up all the small inefficiencies that may be possible to clean up. And this is one of the reason that you basically while you were doing the code generation, you kind of created you just try to be a little bit just remove the complexity, just keep things simple, and you kind of did it for every different location or something like that, and then a separate optimizer later on will basically do this load store coalescing. So in fact, you can imagine that one can even do a DFA pass to just remove extra unnecessary loads and stores. So example, you can just say that, okay, if there's a load followed by a store such that in the middle there is nothing that has been changed, then you just eliminate that. And you can have a separate analysis that just removes all the loads and stores. Within a basic block, people optimizations can help. Thanks for the question. Okay, great. We are also at the end of our time slot. If there's one last question, we can answer that. Otherwise, we are all good. I think this was a very nice discussion session. Great. So in the next week, we are going to talk about the data flow analysis framework. We're going to try to build a theoretical framework for this whole data flow business, so that we can reason about precision guarantees. I mean, so far we have just looked at examples and said, okay, it gives us it gives us a precise solution. It terminates. We have given sometimes examples of why it terminates, or arguments for why it terminates. But then we haven't really given enough arguments to say what I mean by it's giving me a precise solution. And so the theoretical framework will help us answer those questions. And it's going to be a very, I mean, it just helps us understand this whole algorithm space in more detail. So for the next week, please view lecture modules 92. We're doing 5 in a week, so 92 to 96. Yeah.
So I have an unrelated question, not to the modules, but regarding the minor. So do we have a specific date for minor? I mean, I was just asking so that I can plan my office work accordingly.
Sure. So we're not going to have a minor, we're going to have a midterm. There's a semester schedule, which is online. It's at timetable.iitt.ac.in. And so there you'll find the scheduling for the minor, and there are slots for every course, and so our course is no different, and so that's exactly where it's going to that's exactly when it's going to be held in that slot. We're going to hold an online minor, just like we had done in the previous times. So we're going to be so typically the minor slot is 3-4 hours long, and so we're going to schedule like maybe 1 hour slot in that 3-4 hours where we're going to actually administer the exam. Okay, so all the dates and time slots are available on timetable.iitt.ac.in.
Okay, thank you.
I guess the time slot given to us is 18th, and the end time is 12:30 p.m.
Great. Yeah. Thanks.
Okay,
thanks.
thank
Yeah. Thanks. Yeah. So 18th morning. Yeah. Okay. Thank you, and see you next week.